Now we're going to look at position, velocity, speed, acceleration, how these things are related to each other. First of all, position, where something is in relation to something else. Relating to distance often is when we think of position, relating to a distance. Position of an object at time t can be written many ways. Some of the most popular ways, f of t, s of t, x of t, because we talk about moving along a horizontal line and the x direction in a graph is horizontal. Sometimes you need an equation for a free falling object. That looks like this. S of t equals 1/2 g times t squared plus v sub naught t plus s sub naught, where g is the acceleration due to gravity. That's what this is, acceleration due to gravity. And the values are listed here, negative 9.8 meters per second or negative 32 feet per second. The v sub naught is the initial velocity, v at time 0, that's what that means, and s at time 0, initial position. So this may be needed to work some problems from time to time. Now those of you studying physics are going to find this position, velocity, speed, acceleration stuff familiar. Velocity is the rate of change of position, often noted as v of t, which can be both average velocity or instantaneous velocity. Average, of course, being over 2 points in time, an interval, like we talked about with average rate of change, or instantaneous being 1 point in time where it's measured. So average velocity, the v of t would be the change in position over the change in time. The instantaneous velocity would be at 1 point in time, so that's, whoops, excuse me, v of t would be the derivative of the position. Now, no matter what measure it is, since it's velocity, it's still a type of measurement of speed and direction. So sometimes it'll be negative, sometimes it'll be positive. Now, if we talk just straight speed, speed is the absolute value of velocity. Doesn't matter the direction for speed. Like if we talk about a car driving, it's simply the miles per hour, not which direction the car is going in terms of a distance increasing or decreasing. Acceleration is the rate of change of velocity, often denoted as a of t, and it can also be an average acceleration or an instantaneous acceleration. But again, it's a rate of change. So think about it usually like, let's write it like this. V prime of t, or since velocity is the rate of change of position, s double prime of t. We can think of it like that. Since it's the rate of the velocity, we can also think of it graphically as the slope of the velocity, if we have a graph of the velocity. So rate of change, we think of slope. Remember, all of the synonyms like each other. Now, something we're going to get to more in class is when speed is increasing or speed is decreasing. In other words, an object speeds up or an object slows down. And we're going to see why this is true, but ultimately we're going to be looking at the relationship between velocity and acceleration and, excuse me, the signs of those. So just a quick review, starting with position and then taking one derivative, one rate of change takes us to velocity, and one more takes us to acceleration. So thinking of position, velocity, acceleration, if we go in that order for the rates of change. Let's look at an example. A particle moves along the x-axis so that its position in feet is given by x of t. That's its position in feet. What is the velocity at t equals 0? Notice they didn't say average or instantaneous. Whenever it's not specified, it is instantaneous. The instantaneous velocity. Therefore, I know I have to take the derivative, or x prime of t. X prime of t is 3t squared minus 12t plus 9, and I want to know what it is at t equals 0. So x prime of 0, plug in 0 to where t is, and you get 9. We need units, or we do not have a correct answer. Well, what are we measuring? The position over the time. If we think of the derivative as the slope, change in y over change in x, even though it's derivative, the position is the feet. The time is, oh, there it is, in seconds. So it's 9 feet per second. There's our answer for that. When is the particle at rest? What does that mean at rest? Not going anywhere, has a speed of 0, or a velocity of 0. The velocity is 0. Well, we found an expression for the velocity earlier. The velocity is that derivative that we found in part A, which is 3t squared minus 12t plus 9. Let's make that 0. The velocity is 0. Can we solve for t? We sure can. We can factor out a 3, then we can factor the leftovers, t minus 3, t minus 1, and we get t equals 3 or 1. So when is the particle at rest? It's at rest at 1 and 3 seconds. That's when it's at rest. During what time intervals is the particle moving to the left or moving to the right? Well, how it's moving is its rate of change, and right or left is determined by the sign of the velocity. Left is when the velocity is less than 0, right is when the velocity is greater than 0. So let's take what we did in part B, and in these multi-step problems we're usually going to use what we did before. So we found that the particle was at rest at time 1 and 3 seconds. Let's jot a little number line. Nice visual is often helpful. So here's our number line of the t values. We want to know, and I'm going to write the t down here, we want to know the sign of the velocity. We want to know when is velocity positive and negative. Well, our velocity we simplified into 3 times t minus 3 times t minus 1. Let's pick something to test a little bit before 1, like 0. If I plug 0 in for t, this one is a negative number, this one is a negative number. A negative times positive 3 is a positive number. So a positive velocity before 1. Plug in a test value between 1 and 3, like 2. Plug in 2 in here now. So 2 now. That's a negative, that's a positive, and a negative times a positive is a negative. So a negative velocity there. Do I care what the velocity is? No. Sign only. Left, right, that's all I care about. How about a test value of 4? 4 plugged in here instead of 2 gives me a positive. 4 plugged in here gives me a positive, which results in a positive. So positive velocity here. So when is my particle moving to the left and to the right? Well, I see here first it's moving to the right. Is it moving to the right from negative infinity to 1? Does that make sense? Time with negative values? No, it doesn't make sense. So when is it moving to the right? It's moving to the right starting at a logical time. How about time 0? Up to time 1, union with starting at 3, and now they didn't give me any restriction, and time can go on forever, so it's continuously moving to the right, that amount of seconds. When is it moving to the left? In between 1 and 3, so on the interval from 1 to 3 seconds. Positive to the right, negative to the left. D. What's the total distance traveled by the particle? So distance, that's a measure of position. So let's figure out what was its position at the beginning. Position at time 0. Position is the original function. So go back up, take a look at the position, x of 0. So 0 cubed minus 6 times 0 squared plus 9 times 0 plus 11. What do we get when we simplify that? And yes, simplify it because we need to add them up later. 11 feet. It started at 11 feet from the origin. When did it turn around? It turned around at t equals 1. So let's figure out how much did it move. So what is its position at the point when it rested to turn around? So x of 1. Plug the 1 into all those places and we get 15 feet. How much did it move from time 0 to time 1? So it started at 11 feet from the origin, ended at 15 feet from the origin. That's a change of 4 feet. So right now it's traveled 4 feet. So how much it's traveled, I'm going to record over here, it's traveled 4 feet. Well, it turned around again later on at 3 seconds. So at, oh, wait a minute, we don't need to go that far, but we need to figure out where did it stop. So at time 2, x of 2, plug that into our function like we did with the other ones, and we get 13 feet. So how much did it move from 1 second to 2 seconds? 15 feet to 13 feet. It had a change of 2 feet. So it traveled 4 feet and then 2 more feet. How many feet did it travel total? 6 feet total. What's the acceleration of the particle at time 0? What's acceleration? Velocity's derivative, v prime of t. Well, we found velocity. We did the derivative of position earlier and found that the velocity is 3t squared minus 12t plus 9. So what's the derivative of that? Let's take the derivative, 6t minus 12. What is it at time 0? Plug in 0. 6 times 0 minus 12 is negative 12 feet per what? Well, what are we measuring? The velocity divided by the time. What were the units of the velocity? The velocity was in feet per second. The time is in seconds. So how do we represent those units all together? Feet per second times 1 over second, or feet per second squared. So this is 12 feet per second squared. Negative 12 feet per second squared. Finally, F, is the particle speeding up or slowing down at time t equals 0? Well, remember what we were supposed to do. Look at the acceleration, look at the velocity. What is the velocity at time 0? The velocity at time 0, we did that earlier, the velocity at time 0. We did that up here in part A. That was 9 feet per second, so the velocity was 9. I don't care that it's 9. What I care about is that the velocity is greater than 0, positive. What was the acceleration at time 0? Well, we just found that here. It's negative 12. I don't really care that it's negative 12. What I care about is that the acceleration at time 0 is less than 0. So I see the velocity and acceleration have opposite signs. Therefore, slowing down. The particle is slowing down because velocity and acceleration have opposite signs. Last problem on your notes, we're going to do in class. I want you to try to soak this up, study what you did, and we're going to practice this in class. Maybe try to practice it before class or wait till class. See ya in class.